We're going to talk today about a number of things related to energy. We just started looking at energy yesterday, and energy is critically important in our environment, in our ecosystem. It's what drives all of these natural systems. And so we're going to take it back to like a 3rd grade, 6th grade, junior high, freshman year type level of physics to get our minds around it. We're going to take it at the most elemental state and build from there. This to me is one of the most important things. It's also one of the most complex things. But if you can understand this, what we're talking about now, you get the way that 95 or so, 90 to 95% of how weather and climate occur on our planet. And if you know that, you can predict how evolution is going to occur, how organisms are going to be found in different places, what kinds of environmental conditions drive everything on our planet. So it's critically important. It's kind of the cornerstone, literally, of everything, is understanding natural systems, is this thing about the flow of energy and the flow of matter. But today we're going to focus our energy on energy. So, I'm going to give you a definition for energy, and this is a loaded definition with many different parts to it. And I tried to circle the parts that I felt like were the most key. So energy is the ability to do work. So I circled energy because that's what we're talking about. And on the next page, we're going to see energy expressed as a mathematical formula. So I just wanted to keep track of it. But the more important part of the phrase is the ability to do. If I want to do something, I have to have something. In this case, I want to do work. And so in order to do work, I need to have something. What is it that I need to have? I need to have energy. So we just worked our way through that sentence, front ways, backwards, side to side, and every other way you can think about it. Energy is the ability to do work. So when we see energy, we're talking about something that we can do, the ability. So it's going to be expressed as a quantity. We're always going to see energy expressed as the amount of something, the amount. We'll see different amounts, different ways that it's been expressed. We talked a little bit about joules and calories yesterday. We're going to talk about that a little bit more today. But I drew a picture at the bottom. This picture is awesome. I mean, the picture itself sucks, but the picture is awesome because it shows a bunch of things. So here I have energy in all kinds of forms. Energy isn't always found in the same form, but we have the ability to do work. So there's a truck, and there's a block, and there's a rope tying the block and the truck to one another. And so we would agree, this truck has the ability to do work. The most obvious thing is the truck can drive forward and it can pull the block. So we move the block from one physical location to another location. We just did work. But you also see the truck has lights on the front. It's shining light. Light is also a form of energy. You can see the guy is pumping some sweet jams, some tunes coming out. Music, sound waves. That is a form of energy as well. The truck itself is made of matter, and the bonds that keep that matter together also contains energy. So we have energy in all kinds of ways. You can see out of the tailpipe, there's a little hot exhaust coming off. Same thing on the front fender of the truck as well. There's a little bit of heat coming out. Heat is a type of energy. That's a type of energy that we care about a lot. That's what we're going to focus our time on. But energy, the ability to do work. So work is underlined, energy is circled. Let's turn to the next definition. So work. If I'm going to look at energy, it's going to be expressed as a quantity. And this is typically how we're going to think about it. It's the force times the distance. So that ability to do, so we know we'd have to think about, well, how much work were we going to do? That's usually measured in distance. And the force is how you're applying it. So those pieces are the box that goes with the ability to do part. Everybody feel good about that? All right, I need 2 volunteers to come help me. We're gonna display this in a practical sense. 2 volunteers. 3, those 2 girls right there. Come on up. All right. Do you have a watch on, one of you, by the way?
Yeah.
That's what I'm gonna say.
Yeah.
Cool, we'll need that. All right, come on over. Okay, so the textbook of our class, this is just like a cool little metaphor to make or a cool little example to illustrate how important the reading is. There's nothing more important in this class than reading the textbook. This is a beautiful tool. Textbooks are used to help you learn information. So I thought I would use this for this demonstration's purpose to help us learn as well, but I didn't want to damage the book, so I actually wrapped it in this. So our textbook is in here, and it weighs 1.5 kilograms. That number is sort of important. You don't have to write it down, you just got to know it. So I'm going to show. So this has energy in it, the bonds, but we also have some intrinsic energy on this planet. So when this is just sitting in this state, it has potential energy. And why does it have potential energy? Yes.
Staying still.
It's staying still, so it's not moving. So the energy is in a stored state.
Gravity?
The energy comes from gravity. So is there more energy here, or is there more energy here?
First one.
The first one, right? Okay, beautiful. Because I have to go against gravity. So if me picking up the book, I have to do work. I have to work against gravity. I have to apply force to pick up the book, and I have to move at a certain amount of distance. I just did work. Agreed? So we're going to do it in a mathematical way here. So here's what I need. Bree, come over here. Take this, put it on the ground, come and grab this, and then you're going to hand it to me in a second. Write these numbers down because this will go into the mathematics of what we're talking about. So I'm going to have the textbook, and I have it on the ground, and if I want to do some work, in this case the work means I'm going to move it against gravity. So I'm going to move it up into the air. I'm going to apply force against the distance. So the force I'm applying is I'm just going to walk it up here from the point on the ground. Hand me that, please. And I'm going to move it up to 3 meters. Everybody sees this so far, right? Pretty simple. Here you go. So the book right now, I just moved it from 0 to 3 meters. So what is the distance? 3 meters, easy. What is the force?
Gravity.
Gravity. And so for this book at this place where we're standing right now, it's 4 newtons of gravity. So it's 4 newtons times 3 meters, okay? Pretty interesting visual. Beautiful. Okay, great. So, thank you. Stay here though. Going back to our definition, write the numbers down because we're going to do the mathematics. We just did, it was 4 newtons times 3 meters. That equals 12 joules. Joules is a form of energy, and by energy I mean it's a quantity. How much? 12 joules. Everybody feels good about that so far? All right, let me show you something else. We've done 2 parts of a 3-part of this demonstration. So we know about energy, we know about work. Now we're going to think about the force side, because not everything is equal. So say I want to do the same amount of work. So here's the book. I'm going to move it from the ground, and I'm going to climb up just like this, and I take it up, or I can move it really quickly. Which one has more power? Moving it quickly. Let's do a demonstration. Okay, Bree, come over here, and you're going to be my timer, okay? All right, first one I don't really need Bree, but welcome. Hang out. Okay, so I'm going to do the work. The energy is 12 joules, and so I'm going to do this. You're going to time this, okay? You ready? On 3. 1, 2, 3. I'm carrying the book up. I'm doing the work. I'm moving it. I'm applying a force. I'm taking it across a distance. I feel like my 3-meter point is about here, and stop. 11:15. All right, now, Bree, take the book. Hold the ladder, will you? And you're going to time. You can do both, right? Beautiful. Okay, Bree, put it on the ground, and you're going to, take it from the ground, and you're going to toss it up to me. Let's practice. So, on 3. Oh, wait. My gosh. Again. 1, 2, 3. Ah. Okay. So, we're going to do it just like that, and you're going to time it. You ready? So you'll go when we go on 3. You ready, Bree? 1, 2, 3. Stop. 0.8. Beautiful. Round the point after 1 second for math. To make it easy. Thank you, girls. Go on back. Okay, so we applied force and we moved an object across a distance. We just did work. Here's the part 3. Why are these sticking together? Get off of it. There we go. So the application of force is this thing called power. Here's our third definition. And power is described as the amount of work being done. So what was the amount of work from before? 12 joules. Because it was 4 newtons times 3 meters. 12 joules. So it goes 12 joules over the amount of time. The first time was 11, we'll just do 11 seconds. Do the math. And then the other one was 12 joules over 1 second. So which is a higher number? Give me what is it for 12 joules over 1? It's just 12, right? So when Bree threw it to me, the amount of power associated with that amount of work was 12 watts. So, or it was 12 over 1, 12 joules per 1 second, which in this case, it actually equals 12 watts. So when we did it the other way, where I walked it, what's the equation there? It was it should have been 12 over what? 11, 15. So it's about what's the answer? What's the number? 1.0 something. So we had basically 1 watt versus 12 watts. So watts is a form of energy that you've heard about before. The way power is being applied in things like a light bulb. So that's 12 watts. Usually a 60-watt light bulb is what you see. So if that same amount, if I did that 5 times, that'd be the same amount of work as required to just light up a light bulb. Okay? It's also about the same as about 3 calories. So yesterday in the laboratory setting, we were heating up water and we said, well, that's looking at energy as well. And 1 calorie was enough energy to take 1 gram of water up in temperature by 1 degree Celsius. So that amount of work I did carrying the book up, or when Bree threw it, that was 3 calories. So we could have heated up water by 3 degrees Celsius, 1 gram of water. We'd have to do it a little different, but it's the same amount. Does everybody feel good with this so far? Okay. Now, when we were moving it and we did the work and we used the energy and we applied power, when you saw the book flying through the air, what type of energy was that? Kinetic energy. All right, that's going to be important. Here's what I need you guys to do. We're gonna do another demonstration, but we're going to do this one together. So the movement, you can see the kinetic energy, how things are going. The faster you do it, the more you do it, the more energy is there and being used, right? Okay, we're ready. So put your notes right there and come on out. Let's come on out into this space. Leave everything up. Come on out. Again, we're going super elementary, but we want to figure out how all this works, taking it from the simplest state to the more complex. So right now, in this state, how much are you guys moving around? This guy's fixing his shirt, she's rubbing her eyes, but for the most part, are we moving around a lot? So what state of matter do you probably look like right now? Probably a solid state, and then as molecules move around, there's more kinetic energy, and it's the same, all of the mathematics that we just talked about are true for molecules. So we're going to demonstrate what this looks like. I just want you to naturally do what you would do, but here are the rules. I got my drum. Pretty loud. My goal was, somebody told me that we were disrupting math, and I'm like, good. Boo math. I mean, we just did math, but the math we did at school, but that math stinks. Here's what happens. Every time you hear the drum, you're going to take a step. So let's practice. Ready? Drum beat means 1 step. Ready? Oh equals more energy. We have more kinetic energy. Now look at how we're all spread out. And if we kept going, we would keep moving. But it takes heat, and heat is the form of energy. Feel good about that? All right, good. Go back to the Everything we've done so far is baseline. Now we're going to do the cool stuff. We're going to hack this thing about climate and weather. It's going to be outstanding. Give Mr. Hobble a round for the ice. That's beautiful right there. A good man. A good man right there.
Oh, I want to.
Okay. Everybody feels good about energy, work, and power so far, right? Now here's where the rubber meets the road. Energy can be in all these forms: heat energy, electrical energy, sound energy, light energy, but all of the principles are the same. Applying a force across a distance, the more you do that, the more energy you have, the more work you can do. Makes sense, right? Everybody feels that relationship. All right, so now here are three definitions, and we're going to start, and we're going to do this in a specific order because this matters for the way things function on our planet. So the first definition for you, and hopefully you know from the reading, is radiation. Radiation. Our sun is unbelievable, by the way. The sun is outstanding. The sun has all these chemical reactions happening, nuclear fission. It's crazy hot. It's got so much energy, and it's just this giant fireball, and it's pumping all of that energy at the Earth all day, every day, billions of years, 93 million miles away. It's outstanding. All of that energy is coming towards the Earth from the sun to the Earth in the form of radiation, and it flows along visible light and this thing called photons. So keep this in your mind, write it down. So the energy on the Earth comes not from the Earth itself, but we get it from the sun, like this moment right now. You feel it? Feel the energy? Now, this part is kind of tricky. We're going to take it one step at a time. The radiation is hitting the Earth, solar radiation, and it's striking the Earth in the form of photons, and those photons have the ability to excite electrons. So the heat that you feel, by the way, is not the sunlight. The light that you see is the sunlight, but the heat that you feel is not the sunlight. You're not feeling the photons. You can kind of feel it in your skin because it's exciting the electrons on the surface of your skin, but the photons are going into matter on the Earth. Oceans, lakes, grass, tree like I drew here, pavement, all the matter on the surface of the Earth is taking in the photons, and it's exciting the electrons, and because there's so much energy there, it's releasing the energy in the form of heat. So this radiation part only refers to the photons coming towards the Earth, but the heat, I want to make sure that this is very clear because it's important for how all of this functions. The heat that you're feeling in the air and the temperature on our planet, the sun makes us this cozy place to live, but it's because the objects on the Earth are releasing the energy from the sun in the form of heat. That is key. Does everybody understand that so far? Great. So radiation is the first step. Conduction is the second step. All matter has some conductive properties, but some matter is much more conductive than other matter. What kinds of matter is conductive, do you think?
Metal.
Metal is really conductive. Water is fairly conductive. It's not quite as conductive as metal. They're like on a whole different level, but water has some conductive properties, especially when you're thinking about electricity. Metal is definitely the best because of the way that metal, the structure of metals when they get together in a pure way. Yeah. Wood is less than metal, but more than water. So the reason we like metal, we know it's a good conductor, and so we use it all the time in electrical energy. So I tried to draw some power lines here. So copper is a really good wire, and it can conduct electricity, and it can facilitate the flow of energy from one place to another, which is why there's energy when you plug something into a wall. That's how it's flowing, and it's using conduction. But thermal energy goes along conductive things as well. So this is where conductive matters for the Earth. So my definition here is the flow of energy through a material. So we have solar radiation striking the Earth, the ocean, the lakes, the rivers, the rocks, all of that. And the heat energy is flowing from the material to other material. Now there are two types of states of matter that do not conduct very well. Those two states are air or gas and water and liquid. And so that heat energy is really good. The solar radiation comes into the Earth, and then it gets converted to thermal energy, and it gets released into the world, and it happens via conduction. But as soon as it goes from the Earth into the air, it isn't as conductive, and so the flow of the energy is kind of stifled. But we understand about conduction at least, right? Feel good about that? All right, now I'm ready to do the big one. Here's the big one. I was kind of happy the way this turned out, by the way. I grabbed this sheet, and then I ran out of sheets, and I had to write the last page on the cardboard. And I didn't get another sheet because I was like, oh shoot, I'll write it on the cardboard. But then it's different, so I was hoping you would remember, because this one's the most important. But the energy for convection, by the way, you can ignore the circle of arrows for a second, but it comes first from the sun, solar radiation in the form of photons into matter, and that matter conducts the thermal energy from there into the air. And so now that we're in air, and we know the air is not very conductive, and likewise water is not very conductive, the principles are same in both of those states, then the energy is still going to flow from high to low. So keep this in your mind, write it down, and remember it permanently for always and forever, and it's always the same rule. From high to low, high to low. How does it go? From high to low. It goes from high to low. How does it go? High to low, always. Energy always flows from high to low. Keep that in your mind. It's critically important. The good thing is we'll see other systems that happen, and it's always high to low. How does it go? High to low. You got it. High to low all the time. And so the energy via conduction is going from the Earth into the air, from high heat energy, from the states of solid matter and liquid matter of the ocean, into the air, from high to low. But convection, we're actually looking at a slightly different definition, and the distinction is really key. It's the movement of particles, and the movement happens according to these agents of change. Major thing right here, it's density and gravity. So the heat energy is still going to flow from high to low, but it's not going to flow like conduction was, putting it here and it was passing it like a chain reaction. But with convection, it's an actual movement of particles. So if I have a warm particle over here, it's going to move from here to another place. And so we still have the flow of energy from high to low. How does it go? High to low. So it goes from high energy to low energy, but it's actually the movement of the particles, like what you guys did when we were out here. So the particles are moving around, and they're kinetic, and they're moving from one place to another. And as they move around, they get less dense, and they get more spread out. And so if we look at this board, it's the movement of particles due to these agents of change: gravity and density. So if the density is lower, we know what about it? What does that mean? What is our working definition for density? Somebody give me it. What's a working definition for density? If I say density, what are we talking about?
Mass over molecule.
How close the molecules in a substance are, how much stuff is in a given amount of space. And so as they spread out, there's less of them, and they're less subjected to gravity because there's fewer in a small spot, so the agent of change isn't working as much. So you've known this forever since 3rd grade. What rises? And why does the heat rise due to what I just said? What was it? High to low is true. It's less dense, and so it's more spread out. So gravity is not going to act on it. So when the density is lower, it's going to the gravitational pull isn't going to be as much on it. Well, it's the same amount, but it's all spread out, and so they can go up into the atmosphere, or they can move up. Does this make sense so far? You feel good about that? So the density part is the key. So it's gravity and density working together. On the corollary, the opposite is also true. So when particles are cold, they are more dense, they're more packed together, and they're more likely gravity is going to act on them, it's going to pull them down. And so the agent of change, gravity and density working together, cold particles are going to fall. So we still have the exchange of heat energy, agreed? From high to low all the time, but the difference is this time, instead of heat energy just being moved by conduction, chain reaction, or radiation like this flow on waves, it's going to happen according to particles moving from one place to another place. All right, I'm ready for the exciting part of our day. We have a demonstration. Oh my goodness, our man, right there.
Yeah.
All right, we're going to do a little demonstration. And in your notes, according to this demonstration, I need you to keep track of a few things. I want you to make a prediction about what's going to happen each time, and then you're also going to make observations. For some reason, people like to just look at things and not write things down, but you can't look at it later. Make observations. That's what good scientists do. So, in a true magician's kind of way, just to make sure there's no funny business, the hot water is red. Just touch that and confirm to me that it's warm so everybody knows it's true. Feels warm, right? It's warmer. It's not just like atmosphere air or water. It's a little warmer. Let's feel it cold too. You can see there's ice in there. Oh God, it's so hot. Feel the ice. Feels cold, right? Just making sure there's nothing weird. It's a true reaction here. We're trying to make it seem like nature is really cool. I hope you appreciate it. So, the setup for this experiment is exactly the same. We have a red jar with warm water and a blue flask with cool water, and we're going to do it. They're full all the way. So, I brought these down because I felt like they would work really well. In my 10th grade class, we're talking about chemistry and all this right now in the periodic table, and I've been telling my kids the periodic table is the most useful tool ever invented. It's this beautiful thing. So I'm going to use it as a tool for this, but it's a nice illustration. Chemical reactions, man, that's what we're talking about. Beautiful stuff. So Mr. Hobb is going to do the first one here, and what I want you to do is watch it and make a prediction about what's going to happen. So he's going to put the hot jar on top of the cool jar. He's going to invert the hot one and put it on top of the cool jar. So before he removes the laminate, what do you think is going to happen? Make a prediction. Write it down. Make a prediction. This is what good scientists do. We know a few things that can help inform our decisions. How does heat energy flow? High to low. What kind of material are we working with? Substance-wise. What state of matter? It's liquid, and it's water in this case. So, that reaction is set up. I'm going to do the same on this side. No, wait, we'll run it. I forgot how we did it. We'll run it, right? All right, so here we go. So he's going to run it and make observations of what's happening. So he's going to remove the laminate so the water can be on top of one another. Beautifully done. Write down your observations. Writing down nothing is not the same as saying nothing happened, by the way. It's just good science. Sorry, I'll get out of the way. So now this time he's going to do it. and he's going to put the blue jar on top of the red jar. Make a prediction again. What is going to happen? The energy flows from high to low. We're talking about a state of matter that's liquid. We're looking at water specifically. All right, here we go. Make some observations. I'll get out of the way again.